All right, so we're going to be starting with part C, the first part of part C, which is for three tanks in series. Again, we're looking at three tanks where the liquid level in the third tank is controller by adjusting the inlet flow to the first tank using a proportional controller, which is essentially going to be our KC. And this is going to be found by trial and error through numerical solutions of the differential equations. So we're going to set a value for KC essentially in the beginning, but we're going to be adjusting it once we get our graph to show like what's the most stable form of the equation that we need. And this, for simplicity, will be transfer function, and the measurement device is 1. Okay, so let's go ahead back to our code, Colab, and went ahead and imported all of our notebooks as well as other functions that we need, as well as Chemie tools. So we're going to go ahead and import some functions that we need. So starting with the cross-sectional area of our tank, which is going to be set equal to 0.9. And then we're going to have B, which is our proportionality constant. And this is going to be equal to 0.29. And then now we have KC. KC, however, we're just going to be setting it a value, but we're going to adjust it. And again, it's the controller gain. And then we're going to define Qn for our steady state. And we're going to just be setting this equal to 1.12. Let's go ahead and make sure we just run all of this so we don't get any errors as time comes. Okay, so now doing our initial steady state for our tank. So H initial underscore steady state, and we're going to be creating an array for this. So mp.full for 3 of our tanks, and this is going to be for Qn in our steady state divided by our B, proportionality constant. Okay, so now we can go ahead and set our set point, and we'll get into it right after this or in a little bit after this, but essentially the difference of these will be what our error is, and we'll figure that out in a minute. So setting our set point, so H3 set point, the height of our set point in the initial or our initial is going to be equal to H initial steady state. So our initial steady state for our height. And this will be for our very last, this will be taking our very last number of the array essentially, which in this case, we know with code, it's -1. Okay, cool. So we're gonna go ahead and start defining these flow rates and change of height for each of our tanks. So starting by defining our right-hand side for T, V, what we've done before previously, T, V, and our set point, so H3, SP. And of course, we're gonna put our little colon here. Okay, so then setting our H1, H2, and H3 heights of all of our tanks equal to V. Again, I don't want to mess this up in the other video. I had our H3 height of our third tank. I had that labeled as H2 twice. So it messed a lot of things up when we were coding. But moving on, mention our errors. So our error is going to consist of our set point. So our set point minus the height of our third tank, H3. Okay. So now what we can do is define our flow rates for the change of each of every tank. So Q12, for example, is going to be the flow rate from first tank to our second tank, but is going to be essentially the change of it. So Q12 is going to be equal to, in this case, we're using our proportionality constant. The other part of the homework we did not. So B times H1. And what we're going to do for this, let's go ahead and write all of these out so we can kind of explain. So Q23 is going to be equal to B times H2. So our flow rate from our second tank to our third tank. And of course, because this is the change of it, we're using the height of our second tank times our proportionality constant. Okay, so now we can do the flow rate of our third tank, which is equal to our proportionality constant times H3. Okay. Now that we've have this, we can go ahead and define our Qn1. So this is our very initial flow rate. So Qn1 is going to be equal to our steady state flow. So QNSS plus our proportionate, nope, sorry, plus our controller gain constant. So KC, this will be the kind of that variable that's going to be adjusted, and then this will be multiplied by our air. Okay, so now we can go ahead and define, or rather, yeah, define what our change of heights of each one of our tanks are. So starting with DH1, okay, so starting with DH1, this is going to be equal to Qn1 minus Q12. So from our first to second tank, and this is going to be divided by cross-sectional area of our tank. So we're going to do this for our second tank, and in this case, it's going to be from 1 to 2 minus from 2 to 3. Okay. And again, this is going to be divided by our cross-sectional area of our tank. And now for GH3, this is going to be equal to the flow from the second to third tank minus the flow of our third tank. Okay. And then we're going to divide this value by the cross-sectional area of our tank again. Okay. So now, of course, we want to return these values. And returning all of these values, we're going to return D1, DH1, DH2, and DH3. However, we actually do have to put this in the form of our uh, Jack's array. So our should be our JNP. So return JNP dot array. Let's go ahead and connect that. And we have our DH1, DH2, and DH3. Okay. However, I did mess up one thing, and I did this in the other part. I want to connect these. So let's do that to make sure these are all connected here. Let's go ahead and erase that. Okay. So, yeah. Okay, so now we can go ahead and set up our end time Tn, and we're going to set this value equal to 100. And essentially now what we can do is go ahead and solve our differential equation using our solve IVP function. So we're going to say that res equals solve underscore IVP. And again, we're introducing this lambda function, and lambda T and V. And this is going to be operating at the right-hand side for, again, our T and V and TV. And this time is going to be our set point initial. So H3 SP initial. And this is going to be added by 1. Okay. So we're now going to, okay, so now what we're going to want to do is, well, now it's going to be operating from 0, sorry about that, to T end. And then for our initial steady state height, it's going to be operating from 0 to Tn. Okay, that makes a lot more sense. So our method is then going to be equal to, again, Redow, and we're going to set our output to true. We always do. Hence, output equal to true. Okay, looks like I made a mistake here. Yeah, from T, our right hand, lambda from T to V. I believe we do put a semicolon somewhere here that I'm missing. Not exactly sure where. Okay, so my assumption was correct. I probably should have trusted my gut. And this is gonna be a semicolon. Let's go ahead and shift into that. Perfect. So now we want to go ahead and create our plots. So we're going to first want to define what our t-plot is. And like we usually do, this is going to be utilizing our lens space. And we're going to do this from 0 to Tn, what we define as Tn, and then to 500. And then we're going to want to go ahead and actually create our subplots. So fig equals make underscore subplots. And then we'll go ahead and add our scatters. So fig that add underscore scatter, our x is going to be equal to our t plot. Our y is going to be equal to our res dot solve of our t plot, but it's going to be utilizing that second integer. It's going to be pulling our second integer value, and then our name is going to be equal to solve underscore IVP. Okay, believe that looks good. Let's go ahead and update the layout, fig dot update underscore layout. And this is going to be, I'm going to go ahead and set our width equal to 600. And then our height equal to 400. And again, our template equal to plotly underscore dark. Okay, hopefully this looks good. Okay, so perfect. I believe this is what we wanted to see. We have our oscillating curves. However, we're going to go ahead and adjust this controller gain value to, to see kind of what will change from this. Let's go ahead and do that. Okay, so now that we have our graph for this, we want to go ahead and define some values, and we're going to be using these values to kind of compare the numbers, these integers to the oscillation of this graph and see what is the best controller gain KC value to implement to the system, the maximum number we can utilize. So starting with K equal to 1 divided by B, we're all then going to be using this value of K by saying that KC times K divided by 1 plus KC, 1 plus KC times K. Okay, so then we'll then get a value for this. To get our second value, we're going to be using our solvers essentially. So res dot solve for our t plot, and this is going to be for our function of 2, and we're going to be grabbing the very last value, or very last value, or in this case our very last tank. So it's going to be -1, and then we're going to be subtracting this by our res solver function again for t plot, and in this case it's going to not pull our last tank, but instead it's going to pull 0. So okay, something's there should be no parentheses here, so then 0. Res dot solve t plot 2 and 0. Okay, that should be good. Incomplete output. Res dot solve t plot 2 -1 minus res dot solve t plot. Oh, there you go. Okay, so obviously these values are way off. So let's go ahead and start adjusting our KC value. Before we do that, we want to kind of compare the differences between these oscillations when we change the KC value. In this case, our oscillation is growing really strong towards the end, and we actually do not want that. So let's go back and look here. By trial and error through numerical solutions, the maximum value of the controller gain KC beyond which the system becomes unstable. So we want a stable system, okay? So let's go ahead and adjust this. So we're gonna start by doing 2. So let's go and do that. Okay. So as you can see, this is a lot better, but it's not there. We have this integer at 0.87 and this value at 0.98. It's similar, but it's not close. We want to get these numbers pretty close together. And as we can see, the oscillation gets better. We start to oscillate a lot more in the beginning and it dies off. But excuse me, it never gets steady per se. So let's go ahead and change it again. We move from 3 to 2. Now let's go to 1 and shift enter all this. Okay, so as you can see, this becomes a lot better. We have these values which are pretty much identical. We don't really see much oscillation. It starts to oscillate a little bit, and then it kind of eventually starts to become stable around this point. But let's go ahead and, tweak it a little bit more. Let's see what we can essentially come up with. So let's try 1.5. Okay. So this is probably worse because we have at this value at 0.84, this at 0.846. We start to see way more oscillation in this graph, starts to become not stable as it was at 1. So we kind of can tell that 1 is better. So let's go ahead and try 1.25. Right? So these numbers become a lot better. So we start to get that oscillation that gets kind of steady at this point. I would say kind of like the best value for this would be around that 1.2 range, maybe even 1.3 if we try that. But 1.5 is definitely, I would say 1.5 and above is a range that we do not want to see this controller gain value at, and at 1.5 is probably our safest route for this. Okay, so let's finish. Now that we finish that up, we'll move on to the next part of this part. All right, so doing the second part of this part, we're going to be deriving the expressions for the amplitude ratio and phase lag of an open loop transfer function. Essentially, this is our loop here in response to a sine input. Show in detail why the substitution of S equals JW yields the long-term sinusoidal response of the system to a sine input. Okay, we have our loop right here essentially with all of our transfer functions. That equation that we derived from our other part, we have our set points, our error, and we're gonna see we're more or less just gonna be referencing this loop here while we're deriving these equations. But let's go ahead and start with our transfer functions. So as far as transfer functions come, as you can see here from this loop, there are three transfer functions that we're looking at here. We have GC, GP, and GM. GM and GP. And essentially, these are all going to be just G. We're going to kind of state this as a more generalized combination of all three of these transfer functions. So when we reference these transfer functions, we're just going to be referencing it as G. Okay, so now that we have this, we can go ahead and solve for essentially a few things, but we're going to be starting with the equation that G in the Laplace domain is going to be equal to A times omega divided by S squared plus W squared omega. And then this is going to be equal to A1 over S plus B1 and then plus A2. And essentially this is our partial fraction expansion of this term here. And this is going to be S plus B2. And when we uh, combine these or get a conjugate version of these two terms from our partial fraction expansion, we can get CS plus D divided by S squared plus W squared. Okay. Okay, so this is kind of what we're looking for based off of this, based off of our transfer function in the Laplace domain. Okay, so from this we can also derive an equation that sine omega t plus phi is going to be essentially equivalent to omega times cosine phi plus s multiplied by sine phi. Yeah, phi. Okay. All right, so now we can go ahead and make some substitutions using our transfer functions. So again, looking at our transfer function g in the Laplace domain multiplied by a times our omega divided by s squared plus w squared. We're going to then multiply this again by s squared plus w squared omega squared. And this is going to be equal to the summation of I equals 1 of our component. So we're just going to label that as C. And for this, we're going to get AI S squared plus W squared divided by S plus BI. And then this is going to be added by CS plus D. Okay, so now what we can do is call in our complex number J. We've kind of been utilizing I, and we're gonna introduce J in this case. And J is gonna look a little different. Again, looking at our transfer function J, G, we're now gonna be looking at it for JW. So J omega, and this is gonna be multiplied by A omega, and then equal to C times J omega plus D. Okay. We now want to substitute our S for JW. So essentially two things we want to look at from our S. And this was referenced in the problem statement, but S equals JW. And then let's say our S is squared. It's also just going to look like, sorry, S squared equals JW. No, sorry, this is going to look like S squared equals W squared. Okay. Okay, so now we're going to kind of see how this is introduced, but right before that, we have this function again in terms of our JW, and this is going to be equal to J times C over A plus D over AW, A omega. Okay. Um, all right, now that we have that function, let's say that G is equal to Kc times K. So this is kind of introduced into our last part, and we use these values to adjust our oscillating graph. So introducing this now, and actually from the part previously from that would be part A, we introduce this term plus 1. Okay. And remember we did cube that. So now let's rewrite this. But in this case, we're looking at S and replacing it with JW. So this term right here is going to be swapped out. Again, we get the same thing on top, and then we get JW here plus 1 cubed. Okay? So now what we can do is we can rewrite a new equation in terms of our sine and cosines, right? So we have A sine multiplied by our omega times t plus phi. And then this is going to be equal to a bar. Sorry, I don't know if I mentioned, but this is a bar also. A bar times omega times cosine phi plus a bar times s times sine phi. And then this is going to be all over s squared plus w squared. And this is essentially going to be equal to r plus ij. Okay. Okay, so now what we have is an input amplitude, which will essentially give us our output amplitude. And because of this, or not because of this, but from this, we're gonna be finding a bar and phi. So essentially what we're looking for here is finding a bar and phi. Okay. I just want to clarify that and make that important for this part. But as we keep going, we get c squared is going to be added to d over omega squared equals a bar squared. This please can be multiplied by sine squared phi plus a bar squared cosine squared phi. Okay. Um, Now what we'll get is we want to reference a few things and kind of explain what they are in this case. So what we have here is we have C equal A to I, okay? And then from this, we get D over W. Rewriting and simplifying this is going to be equal to AR. And this is in whole. This is a whole or not. So these two separate equations are essentially going to be C over, I believe it is D over W, which will be this term. So D over W equal to our tan now, tan phi. Okay. So eventually what we want to get is our inverse tangent, and we'll see how that kind of comes into play. But I want to explain some of these terms first. So I want to explain these terms. And what we'll get from these terms is a squared times I squared plus a squared r squared equals a bar squared. We can also say that r squared is added by I squared equal to a bar squared divided by a squared. Now, let's say we take the square root of this function. We get r squared plus I squared. Yeah, r squared plus I squared. And this is going to be equal to a bar over a. This is no longer squared in this case. Okay, so what this term right here is going to essentially be referred to is our modulus. And this term is essentially our response over our time, or no, our response, sorry, our response over our input amplitude, okay, of our system, essentially. These two are of our system. Okay, so coming back here, we're almost done here. I want to kind of bring upon this term right here. So what we have, let's say that I over R, if we know that C over D over omega is going to be equal to our tan, I over R is going to be equal to tan phi 2. Okay, so because of that, we can say that, so essentially our phi is then going to be equal to the inverse of tan of our I divided by R over I over R. Okay. Essentially, when what we can kind of um get from this term right here is that to kind of sum it all up is when phi is 180 degrees, we have I over R, this term right here, is less than 1 to satisfy our normal operating conditions. So to satisfy, okay? All right, so that essentially sums this part up. We're going to go ahead and move on to the next part to complete part C. All right, so we are now going to be working on part 3 and 4 of our part C. And I'm gonna kind of do this hand in hand, or we'll somewhat together, but we're gonna be using the expressions derived in C2, generating a Bode diagram, and we're gonna identify the amplitude ratio at the crossover frequency for the system in C1 and explain why the amplitude ratio is 1. So that will come when we actually create our figure or subplot or whatever you want to call it at the crossover frequency when the system is at the limit of stability. And then we're going to go ahead and adjust our KC and see how it shifts the amplitude versus frequency plot multiplicatively and be used to adjust the stability of the system. All right. I'm going to go ahead head and first start that part, and then we'll go ahead and talk about part 4. But going ahead, we first want to start by determining what omega is, and that is just going to be noted as W, and this is going to be equal to NP dot log space And because it's log space, we're going to be doing this for -2, 2, and 1,000 steps, time steps. But this is going to be at 10 to the power of -2 and 10 to the power of 2 because we're in the logarithmic function or space, as you can call it. Let's go ahead and shift enter this. We want to then define what kind of our frequency response is. And this is going to involve our RI, which is our real or imaginary parts. And that's going to be noted as RI. And as we've done from our previous part, we know we've derived this, and this is equal to Kc times K divided by uh divided by no divided by tau times omega times 1j plus 1 because we're referring what the plus we're referring to the frequency response domain plus 1, and then this is going to be the power of 3. Okay, go ahead and shift enter this. Tau's not defined. Go ahead and pause this. Okay, so let me go ahead and actually define what tau is, which is going to be equal to AC divided by B. Let's go ahead and shift enter this. Okay. Hopefully that's correct. We're going to go ahead and move forward from here. And if we have to come back, we will. So we now want to do this for each part and kind of define what each one is. So we want to go ahead and define what R is. And remember we said R is the real part. So we're going to be equaling this function to np.real for our entire Ri function. And we're going to be doing the same thing for I, which is our essentially our imaginary. So np.imag parentheses Ri. Okay, now that we have this, we want to set up our amplitude ratio. So amplitude ratio is going to be defined as AR, and it's going to be using our absolute function. So np.abs for our total RI. Okay. All right. So now we want to set up our phase angle, which is essentially converting our phi to our degrees. So setting up phase, we get phase equal to np dot unwrap. This is essentially just a solver function. And this is going to be for np dot arctan 2. Arctan 2 for our imaginary and real. And then this is going to be multiplied by 180 degrees divided by np dot pi. So just pi. Okay. So now that we have this, we can go ahead and actually create all of our subplots. This is going to get a little bit complicated, just a little bit different than what we usually do, because we're going to be essentially updating not just our layout, but our x-axis and y-axis, but we'll get there in just a second. So first starting by creating our subplots. So fig equals, oh, well, we've already used fig. So fig2 equals make underscore subplots. And our rows are going to be equal to 2, and our columns are going to be equal to 1. Okay. We can then add a scatter. So fig2 dot add underscore scatter. Our x is going to be equal to omega, and our y is going to be equal to our amplitude ratio, and our row is going to be equal to 1, and our column is going to be equal to 1 as well. Okay, so now what we want to do is actually update each one of our axes. So fig dot update underscore x axes, and we're going to be doing this essentially. Well, the reason what we're doing it is we're updating it on a logarithmic function. Remember, we defined what omega was, and we did it on a on based of a logarithmic scale. So this is essentially just going to be type equals log. And we're going to say that our row is going to be equal to 1, and our column is going to be equal to 1 as well. So go ahead and update this as 2. So fig 2. Okay. And of course, we want to do this as well for our y-axis. I'm going to go ahead and just copy and paste this and change this to y. Okay, so now that we have this, we want to essentially create another scatter plot. So fig.to underscore scatter. And for this one, our x is going to be equal to our omega, and our y is going to be equal to phase. And then in this case, we can update our row equal to 2 and our column equal to 1. Okay. So now that we have this, we can actually update our x-axis again. So fig2 dot update underscore x-axis. And what we want to do is, again, put it on a logarithmic function scale and update our layouts per se for our row equal to 2 in this case, and our column equal to 1. Okay. All right, and this is where it might get a little complicated, but we're gonna go ahead and update our layout. And of course, this is gonna start off with what we usually do, which is updating our heights and widths. Start with height or width equal to 400 and our height equal to 600. We're gonna update our template equal to flatly underscore dark. And then we're going to update our show legend, or just our legend equal to false. I'm not sure if you capitalize the plot leaf. Let's go and see. No, you don't. Okay. Show legend equal to false. And then we're going to be essentially updating the amount of tick marks we have. So for the y-axis, so y-axis, y-axis, y-axis 2 is going to be equal to dict. And then D tick. And we're going to be doing this to 60 tick marks essentially. Okay, so let's go ahead and shift enter this and see what we get. Okay, so that looks perfect, I believe. Let me go ahead and pause this and just make sure we're looking at what we need to look at. Okay, so thank God this does look good. And what we want to do now is let's go back and look at this. So we want to explain why the amplitude ratio at 4 is at the crossover frequency. So what is essentially our crossover frequency, right? So let's go and try to see where 1 is. And if we try to find where 1 is, let's try to get as close as we can. This would probably be as close as we can. It's at 0.41. And as you can see, this is at the cusp of instability. So it's right when this graph kind of changes and goes downhill and decreases, which is at 0.41. So this is where, again, where our amplitude ratio at 1 is at the crossover frequency and where the system is at the limit of stability. So instability per se. And what we want to do now is show how our changing KC shifts the amplitude versus frequency plot multiplicatively and can be used to adjust the stability of the system. So let's go ahead and kind of adjust our ratio up here. So we have our KC currently at 1.25. Let's kind of change that. So let's go ahead and change it to 0.25. Okay, so let's go ahead and shift enter all of this. All right, so let's go ahead and try to find where our amplitude ratio is at 1. So I go up here. So kind of, let me go ahead and change this again. Let's do 0.3. Okay, so Okay, so at you can kind of see how it differs again and why kind of the reasoning was multiplicatively or however you call it. But we're looking at this amplitude ratio at one, and as you can see, we were looking at that number at 0.44, and now it's at 0.044. So it's kind of really, really decreased by a ratio of uh, by a division of 10 or I believe, but that's kind of the contrast to where it changes, and you can see how the stability kind of goes out from this point forward and kind of changes a little bit. So yeah, that sums that up. Let's go ahead and now work on generating a plot of the open loop response of the system to a sinusoidal input and show that the amplitude ratio at long times is identical to what is determined via the Bode diagram. Okay. All right, so we're now going to start by inputting our transfer function, so which is GP essentially. So GP is going to be equal to KC. So we've kind of solved for this before, KC times K, and this is going to be divided by our tau function that we defined before, times our S plus 1. Okay. And we can define our function of t and y as a simulation. So we're going to be using sim for our transfer function, GP, and utilizing lambda. So for lambda at t, we're going to be using our np dot sine function, and this is going to be from 1 to the multiplied by t essentially. And then we're going to state that n is going to be equal to 1,000, and our change of time is going to be equal to 0.1. Okay. All right, so now we can go ahead and actually create our subplots. So we can say that fig equals make underscore subplots, and then go ahead and add our scatter. So fig dot add underscore scatter at x equal to t, and then y equal to y. Okay, so now that we have this, we can go ahead and update our layout. Let's also make sure we put these all as fig threes. So now we have fig3 dot update underscore layout at our width of 600, our height of 400, and our template of polydark. Okay, let's go ahead and shift enter this. Okay, so this looks exactly like we want it to look like. And as you can see here from this scatter plot, we have these obvious spikes right here. The first one being the strongest based off of the input, and then it starts to oscillate, right? As you can see here, let's go ahead and look at one of these spikes right here. We see that at 74.6 based off of right here. We want to be looking at the one right here. It gets to 0.029, somewhere in that range. What we want to do based off of this open loop response is essentially see if it's identical to what we've seen in the Bode diagram. So let's go here and see where we can find a point. Let's go ahead and zoom in on that. So as you can see here, at 1, I zoomed in a little bit, try to get as close as we could, but at 1.00462, so at 1, we have it at 0.0294, which is actually essentially like almost exactly the same. So that kind of proves this open loop response that it's identical on this scatter plot compared to our Bode diagram. All right, so that completes this part of the homework. We're gonna go ahead and finish out with part D, deriving a few things. All right.